What if the emptiest corners of the universe weren't empty at all? What if nothingness, the vast, silent void we often dismiss as mere absence, actually had a hidden structure, a blueprint written in the language of absolute zero? We're about to embark on a journey that will challenge everything you thought you knew about space, time, and the very fabric of reality. Picture this: a temperature so cold it defies imagination, where atoms nearly stop moving, and the laws of physics begin to twist in ways that feel almost supernatural. This isn't just theoretical, it's a frontier where science brushes against the edges of philosophy, where the coldest places in existence might hold the secrets to the universe's deepest mysteries. Think about the last time you stared into the night sky, feeling that strange mix of awe and insignificance. Those dark patches between the stars, they're not just empty. They're alive with quantum whispers, particles flickering in and out of existence, dancing to rules we're only beginning to decipher. Absolute zero isn't just a number on a thermometer, it's a doorway. A doorway to a realm where emptiness has shape, where the void isn't passive but pulsates with invisible energy. Scientists call it the quantum vacuum, a sea of potential that underlies everything, from the atoms in your body to the farthest reaches of the cosmos. And here's the wild part: understanding this frozen architecture could rewrite our story of how the universe works. So why does this matter to you? Because this isn't just about physics, it's about the human spirit. For centuries, we've pushed against the boundaries of the unknown, from sailing uncharted oceans to landing on the moon. Now we're probing the architecture of nothingness itself, chasing answers to questions that feel almost primal. What is reality made of? Why is there something instead of nothing? As we peel back the layers of absolute zero, we're not just exploring cold, we're exploring the scaffolding of existence. And by the end of this journey, you'll see the void in a way you never have before. Not as emptiness, but as a canvas, vibrating with possibilities waiting to be uncovered. The paradox of nothingness is that it refuses to be empty. Imagine a room stripped of all furniture, air, even light, pure absence. Right, yet at absolute zero, that theoretical state where all thermal motion stops, something extraordinary happens. The void doesn't settle into perfect stillness. Instead, it thrums with quantum activity, like a silent orchestra playing a symphony we can't hear. Particles blink in and out of existence, borrowing energy from the fabric of spacetime itself, a phenomenon physicists call vacuum fluctuations. This isn't theoretical musing, we've measured it. In labs, scientists observe what's known as the Casimir effect. Two metal plates placed infinitesimally close in a vacuum inexplicably pull toward each other, squeezed by the invisible pressure of these quantum ripples. So what does this mean? If nothingness has structure, then our entire notion of empty space is an illusion. Think of it like the ocean's surface. From a distance, it looks flat and calm, but up close, it's a churn of waves and currents. The quantum vacuum is the same, seemingly barren, yet beneath the surface, it's a seething dance of potential. Even more intriguing, this hidden architecture might hold the key to dark energy, that mysterious force accelerating the universe's expansion. Some theories suggest dark energy could be the quantum vacuum's energy density itself, stretching spacetime like an invisible hand. Here's where it gets mind-bending. Absolute zero isn't just about cold. It's a lens revealing how reality stitches itself together. At temperatures near zero, helium doesn't freeze. It becomes a superfluid, defying gravity to climb walls. Certain materials superconduct, conducting electricity with zero resistance, as if the rules of physics have been rewritten. These aren't quirks, they're clues. They hint that the universe's default state isn't inert nothingness but a dynamic scaffold, vibrating with latent possibilities. This challenges something deeper than physics. It reshapes how we think about existence. We're used to equating absence with passivity, but the quantum vacuum is anything but passive. It's more like the silent hum of a computer's processor, unseen yet essential for everything to function. From the birth of virtual particles to the expansion of the cosmos, the void isn't just the backdrop of reality. It might be the stagehand, the director, even the script. And if we can decode its blueprint, we might finally answer why there's something rather than nothing at all. Absolute zero isn't just a number, it's a frontier where the ordinary rules of physics unravel, revealing a world stranger than fiction. Picture atoms slowed to a near standstill, their chaotic dance chilled until they merge into a single, eerie quantum entity known as a Bose-Einstein Condensate. In this state, particles lose their individuality, behaving like a unified wave, as if the universe itself is whispering secrets about the true nature of reality. Laboratories across the globe push their equipment to the brink, chasing temperatures within a whisper of absolute zero, not just for the thrill of breaking records, but because this frozen edge is where the fabric of existence starts to fray in the most revealing ways. Take superconductivity, for example. At these extreme colds, certain materials suddenly let electricity flow without resistance, as if the usual friction of the universe has been magically erased. This isn't just a laboratory curiosity, it hints at a deeper order hidden beneath the chaos of everyday matter. Or consider superfluidity, where liquid helium defies gravity, climbing the walls of its container as though the very concept of up and down has lost its meaning. These phenomena aren't glitches, they're glimpses into a hidden layer of reality, one where the void isn't empty but brimming with untapped potential. What's truly startling is how these discoveries force us to rethink the nature of nothingness itself. The closer we get to absolute zero, the clearer it becomes that so-called empty space is anything but. Quantum fluctuations persist even in the coldest reaches, particles flickering in and out of existence like cosmic fireflies. It's as if the universe refuses to sit still, even when stripped of all heat and motion. This relentless activity suggests that nothingness isn't a static backdrop, it's an active participant, shaping the behavior of matter in ways we're only beginning to grasp. And here's where it ties back to the grand puzzle: dark energy, the mysterious force accelerating the expansion of the cosmos. Some theorists propose that this energy might arise from the quantum vacuum itself, that sea of flickering particles we once mistook for emptiness. If true, it would mean the coldest places in the universe hold the keys to its largest scale behavior. Absolute zero isn't just a scientific curiosity, it's a Rosetta Stone, helping us decode the universe's most profound mysteries. From the bizarre behavior of ultra-cold matter to the hidden structure of the void, every step closer to this frozen edge peels back another layer of reality, revealing a cosmos far stranger and far more alive than we ever imagined. Those seemingly empty patches of space between stars and galaxies, they're not silent at all. Beneath the illusion of stillness, the quantum vacuum crackles with activity, particles and antiparticles bursting into existence for mere fractions of a second before vanishing again. This isn't some abstract theory. It's a fundamental feature of reality, confirmed by experiments like the famous Casimir effect, where the sheer pressure of these fleeting particles can move physical objects. Imagine a quiet pond at night. Its surface looks smooth, but peer closer, and you'll see tiny ripples dancing across it, born from invisible forces. Quantum fluctuations are like those ripples, tiny tremors in the fabric of space-time itself. What's truly astonishing is how these ephemeral particles might hold the universe together. Think of them as cosmic glue, mediating forces like electromagnetism and even gravity. Without these brief, energetic sparks, the structure of atoms would unravel, and matter as we know it would cease to exist. It's almost poetic. The very thing we call emptiness is what stitches reality into coherence. Some physicists speculate that these fluctuations could even be the seeds of cosmic inflation, the explosive expansion that shaped the early universe. If true, then the grand tapestry of galaxies, stars, and planets might trace back to these ghostly flickers in the void. But here's where it gets even stranger. Quantum fluctuations challenge our most basic assumptions about cause and effect. Particles appear and disappear without any discernible reason, as if reality itself is improvising. This isn't randomness, it's a deeper order we're only beginning to decode. Some theories suggest these fluctuations could be holographic projections, echoes of information encoded on the boundaries of the universe. Others propose they're evidence of hidden dimensions vibrating just beyond our perception. Whatever the answer, one thing is clear: the void is anything but passive. It's a dynamic stage where the universe constantly reinvents itself, moment by moment. So what does this mean for us? If the vacuum of space is this alive, then nothing might be the most fertile ground of all. From the birth of virtual particles to the acceleration of cosmic expansion, the quantum vacuum isn't just background noise, it's the unseen architect of reality. And every time we probe deeper, we're not just studying cold, empty space. We're eavesdropping on the universe's quietest, most profound conversation. Dark energy isn't just a mysterious label in a physics textbook. It's the universe's most enigmatic architect, stretching the cosmos apart at an ever-increasing speed. Picture a balloon inflating, but instead of slowing down, each breath makes it expand faster, as if some unseen hand is pumping energy into the very fabric of space. This isn't science fiction. It's the reality we live in, where galaxies aren't just drifting apart, they're being pushed by a force so pervasive it makes up nearly 70% of the universe's energy budget. And here's the twist: the source of this cosmic push might be hiding in plain sight, woven into the void itself. The quantum vacuum, that seething sea of virtual particles we once called empty, could be the engine behind dark energy. Imagine the vacuum as a vast, invisible spring, constantly under tension. Every cubic centimeter of space, no matter how empty it appears, hums with this latent energy. According to some theories, dark energy arises when that tension isn't perfectly balanced, creating a kind of negative pressure that stretches space-time from within. It's as if the universe is built on a foundation of springs, each one adding a tiny push to the expansion. But there's a problem. When physicists calculate how much energy the quantum vacuum should contribute, the numbers are staggeringly off by a factor of 10 to the power of 120. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics, yet the voids between galaxies might hold clues. These vast, seemingly barren regions aren't just gaps, they're dynamic arenas where dark energy's effects are magnified. Without the gravitational pull of matter to counteract it, dark energy dominates here, sculpting these voids into ever larger bubbles of near-nothingness. Some researchers speculate that these voids aren't truly empty but threaded with an invisible lattice, a cosmic foam of energy fluctuations that guide the large-scale structure of the universe. If true, then the emptiest places in existence might be the very workshops where dark energy does its most transformative work. This reshapes how we think about the universe's fate. If dark energy keeps accelerating expansion, could it one day tear spacetime apart? Or might the vacuum's energy suddenly shift, collapsing the cosmos in a reversal we can't yet predict? These aren't just thought experiments, they're questions that force us to confront the idea that nothingness isn't passive. It's a dynamic, creative force, as capable of building as it is of erasing. And as we peer deeper into the void, we're not just mapping emptiness, we're decoding the universe's quietest, most powerful language, one that might finally explain why everything exists at all. The holographic principle turns everything we know about reality upside down. Imagine the entire universe, every star, every planet, even your own body, not as three-dimensional objects but as a shimmering projection, like a movie playing on the surface of an impossibly vast cosmic film. According to this mind-bending idea, all the information that makes up our three-dimensional world could be encoded on a two-dimensional boundary at the edge of space, a sort of universal hard drive where data is stored with pixel-like precision. And here's where absolute zero comes in. This unimaginable cold might be the pristine surface where reality's code is etched. Think of it like a hologram on your credit card, tilted, and the flat surface suddenly gives the illusion of depth. The universe could work the same way, with the void acting as the ultimate projector screen. At temperatures near absolute zero, where quantum fluctuations quiet but never fully disappear, the fabric of space-time might become stable enough to hold this cosmic encryption. Physicists studying black holes stumbled onto this idea when they realized the information swallowed by these gravitational monsters isn't lost forever. It's smeared across their event horizons, the point of no return, like ink on a spherical parchment. If a black hole's surface can store data, why not the entire universe? This reshapes nothingness into something extraordinary. Instead of empty space, we're looking at the universe's operating system, a frozen hard drive where every law of physics, every particle, every force is written in a language we're just beginning to translate. The quantum vacuum's fluctuations could be the ones and zeros of this cosmic code, flickering patterns that translate into the richness of our 3D world. Even more astonishing, this might solve one of physics' biggest headaches, the clash between gravity and quantum mechanics. If gravity isn't fundamental but emerges from these 2D data patterns, like heat emerging from the motion of atoms, then the holographic principle could be the missing link in our theory of everything. But how do we test such a wild idea? Laboratories studying ultra-cold quantum systems are already seeing hints. When certain materials are chilled to near absolute zero, their electrons start behaving as if they're trapped in fewer dimensions, their movements constrained to flat, sheet-like pathways. It's as if the colder things get, the more reality remembers its true, flattened nature. Meanwhile, telescopes scan the cosmic microwave background, the afterglow of the Big Bang, for anomalies in its pixelation, subtle distortions that might reveal the universe's underlying grid. If the holographic principle holds, then absolute zero isn't just the absence of heat, it's the quiet hum of the universe's processor, the state where information is most perfectly preserved. The void becomes the ultimate archive, a library written in quantum frost. And us, we might just be characters in a story the cosmos is telling itself, projected from the coldest, emptiest, and most profound medium imaginable. Black holes aren't just cosmic vacuum cleaners, they're the universe's most extreme laboratories, places where gravity bends the rules of reality until they snap. At their event horizons, the boundary where light itself surrenders to gravity's grip, time slows to a crawl and space stretches like taffy. But it's what lies deeper that truly bends the mind, the singularity, a point of infinite density where the laws of physics as we know them cease to exist. Here, in this realm of pure paradox, the very concept of nothing takes on new meaning. Some theories suggest singularities aren't just destructive, they might be creative, forging new physics in their crushing depths. Consider the information paradox, one of the fiercest debates in modern physics. When matter falls into a black hole, does it vanish forever, erased from the universe's ledger, or is its information preserved, scrambled like an encrypted message across the event horizon's surface? This isn't just academic. It cuts to the heart of whether reality is fundamentally predictable or if black holes are cosmic shredders, permanently deleting the universe's secrets. The holographic principle offers a startling answer. What we perceive as three-dimensional destruction might just be data getting flattened, like a book pressed into a single page. If true, black holes don't annihilate information, they compress it, encoding it in a frozen, two-dimensional script at absolute zero's edge. Now tie this back to nothingness. Black holes aren't empty, they're saturated with quantum activity. Near the singularity, virtual particles flicker in and out of existence, their energy borrowed from the fabric of space-time itself. In this chaos, some physicists see echoes of the quantum vacuum's hidden structure, where empty space buzzes with the same restless energy. The difference: a black hole's gravity amplifies these effects to extremes, turning the void's subtle whispers into deafening roars. It's as if black holes are cosmic magnifying glasses, revealing the quantum vacuum's true nature under conditions too intense to ignore. But here's the twist: black holes might also be time capsules. As they evaporate over eons via Hawking radiation, they could release traces of the information they swallowed, like cosmic messages in bottles. If we could decode that radiation, we might uncover how absolute zero's architecture preserves information against all odds. Some models even suggest that black holes, in their final moments, become perfect mirrors of their birth states, a loop where destruction and creation blur. So what does this mean for the void? Black holes force us to confront that nothingness isn't passive, it's dynamic, a stage where information dances between destruction and preservation. They hint that the universe's coldest, emptiest corners might be its most inventive, forging new physics in the crucible of extremes. And if we ever unravel their paradoxes, we might finally understand how reality is woven from the fabric of nothing at all. Entropy is often called time's arrow, the relentless force that pushes the universe toward chaos, turning stars to dust and order into randomness. But what if the ultimate state of order isn't found in structure or symmetry, but in the void itself? At absolute zero, where atoms grind to a near halt, entropy doesn't vanish. It hits its lowest possible point, as if nothingness is the universe's most pristine ledger, a frozen record of perfect balance. This flips our intuition on its head. We think of emptiness as passive, but thermodynamics suggests it might be the cosmos' most disciplined architect. Picture a sandcastle on a beach. Left alone, wind and waves will scatter it, grains drifting into disorder. That's entropy at work. Now imagine cooling that sand to absolute zero. The chaos stops, every grain settles into place, locked by the absence of thermal energy. This isn't just a metaphor. In superconductors chilled to near zero temperatures, electrons pair up and move in flawless unison, as if the universe has hit pause on its usual messiness. The void, it seems, isn't chaotic. It's the one place where entropy's march falters, where the universe's tendency toward disorder meets an immovable wall. But here's the twist: even in this frozen order, quantum mechanics keeps the void alive. Particles still flicker in and out of existence, defying the classical idea of perfect stillness. So is nothingness truly ordered, or is it a different kind of chaos, one where randomness plays by subtler rules? Some theorists argue that the quantum vacuum's fluctuations are entropy's final frontier, a zero-point energy that keeps the void from ever being truly quiet. It's as if the universe insists on keeping a whisper of unpredictability, even in its most subdued state. This duality, order and chaos intertwined, might hold the key to dark energy's puzzle. If the vacuum's energy density is driving cosmic expansion, then entropy's grip isn't just loosened at absolute zero, it's reshaped into something generative. Think of it like a frozen river. Beneath the ice, currents still flow, unseen but powerful. The void's apparent order could be masking a deeper dynamism, one that fuels the universe's growth while resisting entropy's usual decay. What does this mean for us? If nothingness is the template for cosmic order, then the universe's fate might hinge on this silent balance. Will expansion stretch spacetime until even quantum whispers fade, leaving a true, eternal zero? Or will the vacuum's hidden activity keep reality alive in ways we can't yet imagine? Entropy's arrow might point toward chaos, but the void whispers back with a paradox. In the coldest emptiness, there's a rhythm, a structure, a blueprint for existence itself. Time doesn't just slow near absolute zero. It transforms into something unrecognizable. Picture the most precise atomic clock ever built, its ticks governed by the steady vibrations of cesium atoms. Now plunge that clock into the deep freeze, chilling it to within a fraction of absolute zero. The atoms, robbed of thermal energy, nearly stop moving, and the clock's ticks stretch into sluggish, drawn-out pulses. It's as if time itself is sinking into quicksand, each second straining against an invisible weight. But this isn't just a laboratory curiosity. It's a window into one of physics' most haunting questions. If time grinds to a halt in the coldest reaches of the universe, does nothingness exist outside of time altogether? The idea isn't as far-fetched as it sounds. Einstein taught us that time and space are woven together into a single fabric, but near absolute zero, that fabric might fray in unexpected ways. Some theories suggest the quantum vacuum, that seething, empty space we've been exploring, could be a timeless scaffold, a stage where the drama of reality plays out without being bound by time's usual flow. Think of it like the background hum of a recording studio, silent to the audience but essential for the music. The void might be the universe's silent foundation, a realm where time's arrow hasn't yet been drawn. Here's where it gets even stranger. In quantum mechanics, particles can become entangled, their fates linked across vast distances instantaneously, as if time and space don't apply to their connection. At absolute zero, where thermal noise fades to almost nothing, these quantum bonds might dominate, stitching the void into a timeless web. Some physicists speculate that this could explain why the laws of physics appear so finely tuned for life, because the nothingness beneath them isn't governed by time's randomness but by a deeper, more enduring order. But if the void is timeless, what does that mean for us? We're creatures bound by seconds and seasons, our lives measured in heartbeats and rotations of the Earth. Yet every atom in our bodies emerged from that same timeless vacuum, forged in stars whose fuel was once quantum flickers in the dark. It's a humbling thought. We're not just in the universe, we're of it, shaped by a void that might operate on a clock we can't even perceive. And if we could peer deep enough into absolute zero's frozen heart, we might catch a glimpse of reality's true tempo, not the ticking of a clock, but the silent, endless hum of nothingness itself. Superconductivity is like discovering a hidden rulebook of the universe, one where electricity flows without the usual resistance, as if the laws of physics have temporarily relaxed their grip. Imagine a wire chilled to near absolute zero, so cold that electrons pair up and glide through it like synchronized swimmers, never colliding, never losing energy. This isn't just a laboratory trick. It's a fundamental shift in how matter behaves when stripped of thermal chaos. The implications are staggering. Power grids without energy loss, levitating trains gliding effortlessly, MRI machines with unprecedented precision, all possible if we could unlock superconductivity at more practical temperatures. But beyond the technological marvels, this phenomenon whispers something profound about the nature of reality itself. The secret lies in something called Cooper pairs. At ultra-cold temperatures, electrons normally repelled by their identical charges suddenly form fragile partnerships, bound together by vibrations in the material's atomic lattice. It's as if the void between atoms becomes a dance floor where particles move in perfect harmony, their usual friction erased. This isn't just a quirk of certain metals, it's a glimpse into a deeper order, a state where the universe's usual noise fades away, revealing a hidden symphony. Some theorists even suggest that superconductivity mirrors the behavior of the quantum vacuum itself. That seething nothingness we've been exploring, where particles flicker in and out of existence with similar coordinated randomness. What's truly mind-bending is how this ties back to cosmic scales. Neutron stars, those dense remnants of supernova, are thought to harbor superconductive cores where protons flow without resistance in a swirling quantum soup. Even more intriguing, some models propose that space-time itself might exhibit superconductive-like properties in extreme conditions, with gravitational waves propagating without dissipation. If true, then the same physics that lets electrons glide effortlessly in a lab might also govern the behavior of the universe's largest structures. It's as if absolute zero isn't just a temperature, it's a key to deciphering a hidden layer of reality, one where friction is an illusion and the void hums with unseen coherence. Yet the puzzle isn't fully solved. High-temperature superconductors, materials that defy expectations by operating at warmer, though still frigid conditions, hint that we're missing a piece of the theory. Could these materials be tapping into a different kind of quantum order, one where the void's architecture is more complex than we imagined? Every breakthrough, from ceramic compounds to metallic hydrides, feels like peeling back another layer of a cosmic onion, revealing how much we still don't understand about nothingness. So where does this leave us? Superconductivity isn't just about zero resistance. It's a portal into the universe's underlying elegance. It suggests that beneath the apparent chaos of particles and heat, there's a realm of perfect coordination, a silent rhythm waiting to be harnessed. And as we inch closer to room temperature superconductors, we're not just chasing better technology, we're probing the universe's deepest blueprints, written in the language of cold and void. Zero-point energy sounds like science fiction, an infinite wellspring of power hidden in the vacuum of space itself. Yet quantum mechanics insists it's real. Even at absolute zero, when all thermal motion ceases, the universe refuses to sit still. Particles jitter with residual energy, a ceaseless quantum fizz that permeates every cubic centimeter of so-called emptiness. This isn't just theoretical. We've measured it. The Casimir effect, where metal plates in a vacuum inexplicably attract, proves zero-point energy isn't an abstraction. It's a tangible force, nudging objects with the pressure of virtual particles popping in and out of existence. The audacious idea, tapping this energy, imagine a civilization powered not by stars or fossil fuels, but by the boundless hum of the quantum vacuum. The math suggests the energy density in empty space is staggering enough, in theory, to boil Earth's oceans in a heartbeat if fully harnessed. But here's the catch: extracting it isn't like drilling for oil. Zero-point energy isn't concentrated. It's woven into the fabric of spacetime itself, a diffuse sea of potential that resists containment. Some proposals involve manipulating Casimir cavities or exploiting quantum fluctuations with nanostructures, essentially skimming energy from the void's restless surface. Others speculate about exotic materials that could act as cosmic sponges, soaking up vacuum energy like a towel dipped in an invisible ocean. Skeptics, of course, dismiss this as wishful thinking. The laws of thermodynamics seem to forbid perpetual motion machines, and zero-point energy extraction risks violating energy conservation unless you redefine what conservation means on quantum scales. Yet the allure persists. NASA has toyed with concepts like the quantum vacuum plasma thruster, a propulsion system that theoretically pushes against the vacuum itself. While results remain controversial, the ambition is clear. The void isn't just empty space to cross, it's a fuel source waiting to be unlocked. What makes this more than a pipe dream is how zero-point energy blurs the line between science and philosophy. If the vacuum brims with untapped power, then nothing is a misnomer, a relic of human intuition, not physical truth. The universe's true baseline isn't stillness, it's a simmering potential, a reminder that reality's most fundamental layer is anything but passive. And while we may never build a zero-point power grid, the pursuit alone reshapes our cosmic perspective. The void isn't a barren wasteland. It's a dynamo humming with the energy of existence itself. The vacuum catastrophe is one of physics' most embarrassing open secrets, a calculation so wrong it defies common sense. According to quantum field theory, empty space should be bursting with energy, a seething ocean of infinite density. Stack up all the possible vibrations of quantum fields, add their contributions, and the numbers explode into nonsense. If the math held, the vacuum's energy would curve space-time so violently that the universe would have ripped itself apart moments after the Big Bang. Yet here we are in a cosmos that's not only stable but accelerating outward. Clearly, something's missing. This isn't just a minor glitch, it's a gaping hole in our understanding of reality. Think of it like trying to weigh a feather with a scale built for planets. The tool we're using, quantum field theory, works brilliantly for particles and forces, but when applied to the void itself, it spits out answers 120 orders of magnitude off. That's like predicting a candle's glow would outshine the sun. The discrepancy isn't just embarrassing, it hints that emptiness might operate by rules we haven't yet imagined. Some theorists argue the solution lies in supersymmetry, a hypothetical doubling of nature's particles that could cancel out runaway infinities like cosmic bookkeeping. Others propose the vacuum isn't truly empty but structured in ways that hide its energy, like a sponge soaked in invisible ink. Then there's the radical idea that gravity, the universe's architect, behaves differently at quantum scales, softening the vacuum's ferocious buzz. But here's what's truly humbling. The vacuum catastrophe forces us to confront how little we grasp about nothing. We've built telescopes to peer across billions of light years and colliders to smash particles at near light speed, yet the empty space between atoms remains a riddle. Maybe the answer isn't in the math but in the question itself. What if we're asking the wrong thing, assuming nothingness is simple when it's the universe's most sophisticated trick? This isn't just academic. Dark energy's grip on cosmic expansion suggests the vacuum's hidden energy is real, just far subtler than our theories predict. Like an iceberg, most of its influence lurks beneath our equations. Until we solve this puzzle, we're missing a chapter in the story of existence, one where emptiness isn't the absence of everything, but the stage for physics' next revolution. String theory doesn't just reimagine particles, it turns the universe into a grand cosmic orchestra. Picture the tiniest building blocks of reality, not as dots but as infinitesimal strings, vibrating at different frequencies like the strings of a violin. The pitch of these vibrations determines whether a particle becomes an electron, a quark, or even a photon. But here's where it gets wild. If particles are musical notes, then the void, absolute zero's domain, might be the concert hall itself, resonating with harmonies we can't yet hear. At temperatures near absolute zero, where thermal noise fades to a whisper, these vibrational patterns could become eerily clear. Think of it like cooling a room until you can hear the faintest hum of a distant engine, except in this case, the engine is the fabric of space-time, thrumming with the latent energy of strings too small to see. Some versions of string theory suggest that the quantum vacuum isn't truly empty but threaded with these vibrations, a hidden dimensionality where up to 11 layers of reality fold in on themselves like the overtones of a chord. This isn't just poetic speculation. The mathematics of string theory imply that the universe's most fundamental layer might be built from these oscillations, with the void acting as a kind of cosmic tuning fork. When particles interact, it's not a collision in the traditional sense, it's more like two musical notes harmonizing or clashing, their vibrations weaving the tapestry of forces we experience as gravity, electromagnetism, and more. Even the bizarre behavior of matter at absolute zero, like superconductivity or superfluidity, could be echoes of these deeper vibrational rules, but the real mind-bender. String theory proposes that these strings don't just vibrate in the 3 dimensions we know. They thrash through hidden dimensions, curled so tightly that we've never detected them. Absolute zero might be the key to unmasking these extra layers. In the absence of thermal chaos, the subtle shapes of these dimensions could imprint on quantum phenomena, like a frozen lake revealing the contours of the ground beneath it. Experiments with ultra-cold atoms are already hinting at exotic behaviors that don't fit standard models. Could these be glimpses of strings dancing in higher dimensions? Critics argue string theory is untestable, a beautiful idea without evidence, yet its vision of the void is irresistible, not as barren emptiness, but as a dynamic medium where every nothing hums with the potential for everything. If true, then absolute zero isn't the end of motion. It's the purest form of music, a silent symphony written in the language of vibrating strings, and we might just be one breakthrough away from tuning in. The multiverse isn't just about infinite versions of you, it might also mean infinite flavors of nothingness. Picture a cosmic tapestry where each thread is a separate universe, each woven with its own unique laws of physics. In one, absolute zero might be colder than we can fathom, freezing time itself into crystalline stillness. In another, the vacuum could simmer with a different kind of quantum froth, where particles flicker in patterns we'd find unrecognizable. If true, then the void isn't a universal constant, it's a chameleon, shifting its nature depending on where you stand in the multiverse's labyrinth. Consider the anthropic principle, the idea that our universe's laws seem finely tuned for life because, well, we're here to observe them. If the multiverse exists, most of its universes might be stillborn, too hot, too chaotic, or too empty to spawn even a single atom. But in the rare ones where conditions align, like ours, nothingness might take on just the right architecture to allow stars, planets, and life to emerge. Some theories suggest that the energy density of the quantum vacuum, the very thing driving dark energy, could vary wildly across universes. In some, it might be too weak to spark cosmic expansion, leaving reality collapsed in on itself. In others, it could rip space-time apart before the first molecule forms. Our universe, it's the Goldilocks zone where emptiness is neither too passive nor too aggressive, but just right for complexity to unfold. This raises a haunting question. If other universes have different versions of nothingness, could some harbor structures we can't even conceive? Imagine a cosmos where the vacuum isn't a sea of virtual particles, but a lattice of frozen energy, or where absolute zero isn't the end of motion, but the start of an entirely new physics. String theory hints at this, proposing that the shape of hidden dimensions could vary across multiverses, altering how quantum fields, and thus emptiness, behave. In one universe, the void might resonate like a plucked string. In another, it could hum with the dissonance of a broken chord. Yet the most tantalizing possibility is that these alternate voids might leave traces. Cosmic inflation, the theory that our universe ballooned from a quantum fluctuation, suggests that other bubble universes could exist alongside ours, separated by unimaginable distances. If two bubbles ever brushed against each other, their differing vacuum energies might have left scars in the cosmic microwave background, ancient fingerprints of a collision with another reality's nothingness. Telescopes are already scanning for these anomalies, hunting for irregularities that could hint at a multiverse's existence. What does this mean for us? If nothingness isn't universal, then reality is far stranger and richer than we imagined. The void isn't just the absence of something, it's a canvas painted with whatever rules its universe imposes. And if we ever prove the multiverse is real, we won't just be mapping new worlds, we'll be decoding the infinite ways existence can whisper to itself in the dark. Consciousness might seem like the last thing you'd associate with the void after all. How could emptiness think? Yet some daring theories suggest the quantum vacuum isn't just a backdrop for reality. It could be a participant, even a medium, in the mystery of awareness. Imagine the universe's coldest, emptiest reaches not as barren wastelands but as vast, interconnected networks humming with proto-conscious activity. This isn't mysticism, it's a fringe but growing field where physics brushes against philosophy, probing whether the void's hidden structure might hold clues to the nature of mind itself. Take the idea of panpsychism, the view that consciousness isn't exclusive to brains but is a fundamental feature of reality, like mass or charge. In this framework, even the quantum vacuum's flickering particles might possess a whisper of experience, not as rich as human thought but as a kind of raw, elemental awareness. It sounds wild, but consider this. The brain's neurons communicate via electrical impulses, which are just coordinated movements of electrons, the same particles that dance in the quantum vacuum. Could the difference between mind and void be one of degree, not kind? Some researchers speculate that under the right conditions, like the near-perfect order of absolute zero, these proto-conscious flickers might synchronize, creating more complex subjective experience. Then there's the holographic principle's eerie implication. If the universe is a projection from a two-dimensional boundary, where all information is stored like pixels on a cosmic screen, then consciousness might not be confined to our skulls. Instead, it could be a process woven into the fabric of spacetime itself, with the quantum vacuum acting as the substrate. Think of it like a radio tuning into a station. The brain doesn't generate consciousness but receives it, filtering the void's latent information into coherent experience. Experiments with ultra-cold quantum systems show particles behaving as if aware of their entangled partners across vast distances, as though information flows through hidden channels in the vacuum. Skeptics, of course, dismiss this as speculative overreach. Yet the hard problem of consciousness, why and how physical processes give rise to subjective experience, remains unsolved. Traditional neuroscience struggles to explain how mere matter creates the vividness of a sunset or the sting of grief. If the void's architecture holds even a fraction of the answer, it could rewrite not just physics but our understanding of existence. Picture a future where we manipulate vacuum states to interface with consciousness directly, or where AI doesn't simulate awareness but taps into the universe's native capacity for it. This isn't just about solving puzzles, it's about reimagining our place in the cosmos. If the void and consciousness are linked, then every thought might ripple through the quantum vacuum, every moment of awareness a note in a grand, frozen symphony. And as we peer deeper into the abyss, we might find it peering back, not with eyes, but with something far stranger, the silent, shimmering potential of a universe that knows itself. Simulation theory flips the script on nothingness entirely. What if the void isn't an absence, but the universe's way of saving RAM? Imagine reality as an ultra-advanced simulation, where every star, every atom, is a line of code in some cosmic computer. In this scenario, absolute zero isn't just cold. It's the equivalent of a blank pixel, a stretch of the program left unrendered to conserve processing power. The quantum vacuum's flickering particles, maybe they're not fundamental at all, but glitches background processes briefly flashing into view when the system's attention wavers. Think of it like a video game. When you're not looking at a specific part of the map, the game doesn't bother loading it in full detail. It's still there, but simplified, a placeholder until you turn your gaze back. Could the universe work the same way? The regions we call empty might be the cosmic equivalent of low-resolution zones, where the simulation only bothers to calculate the bare minimum, a hum of quantum fluctuations, just enough to keep the math consistent. Even dark energy's mysterious push could fit this model, an algorithmic tweak to prevent the simulation from collapsing under its own complexity, like a programmer adjusting frame rates to keep the game running smoothly. This idea isn't just sci-fi speculation. Some physicists argue that if the universe is a simulation, we'd expect to find signs in the fabric of reality itself. Tiny, pixel-like limits to how small distances can be divided, or subtle asymmetries in the cosmic microwave background hints that space-time isn't perfectly continuous, but built from discrete chunks like a digital image under a microscope. Absolute zero, then, becomes the ultimate stress test for the simulation. At these extremes, where the usual noise of heat fades, the underlying code might show through. Superconductivity's flawless electron dances, that could be the system's optimized physics engine kicking in, cutting computational corners where friction isn't needed. But here's the kicker. If nothingness is just unrendered code, then reality's deepest mysteries, dark energy, quantum entanglement, even consciousness, might not be features of the universe, but artifacts of the simulation. The void isn't empty, it's the debug mode of existence where the rules relax enough to reveal their artificial seams. And if that's true, then absolute zero isn't the end of the story. It's the debug log waiting to be read. Quantum entanglement defies every instinct we have about how the universe should work. Picture two electrons born from the same quantum event, then flung to opposite ends of the galaxy. Change the spin of one, and the other instantly mirrors that change, no signal, no delay, as if space and time don't apply to their connection. Einstein called this spooky action at a distance, but today we know it's real. Laboratories have confirmed it repeatedly, with particles separated by hundreds of kilometers still dancing in perfect, inexplicable sync. What if this phenomenon isn't just a quirk of quantum mechanics, but a clue that the void itself is threaded with invisible ties, a hidden scaffolding we can't yet see? At the heart of entanglement lies a paradox. Information seems to travel faster than light, violating relativity's sacred speed limit. Yet there's no energy or matter being exchanged, just a correlation, as if the particles are two ends of a single, stretched-out entity. Some theorists propose that this glue isn't a force in the traditional sense, but a feature of spacetime's underlying geometry. Imagine the universe as a sheet of paper crumpled into hidden dimensions. Two dots on the surface might appear far apart, but if the paper folds just right, they could touch. Entanglement might work the same way, with particles connected through shortcuts in the quantum vacuum's fabric, shortcuts we can't perceive because they exist outside our three-dimensional view. Here's where absolute zero comes in. In the freezing quiet of near-zero temperatures where thermal noise fades, these quantum threads might become more visible. Experiments with ultra-cold atoms show entangled states lasting longer, as if the void's usual chaos no longer drowns out their delicate harmony. It's like trying to hear a whisper in a storm versus a silent room. The colder the environment, the clearer the whispers of entanglement become. This hints that the phenomenon isn't just between particles, it's mediated by the void itself, a silent conductor orchestrating their movements. But the real shocker, entanglement might not be rare. Some models suggest the quantum vacuum is a vast, seething network of these invisible links, with particles constantly pairing and unpairing in a dance we've only glimpsed. If true, then what we call empty space is more like a cosmic switchboard, buzzing with instantaneous connections that stitch reality together. Dark energies push, the universe's expansion, even the way matter clumps into galaxies. All of it could trace back to this web of quantum ties humming beneath the surface. So where does that leave us? Entanglement forces us to confront that nothingness isn't passive, it's dynamic, a medium that transcends distance and time. And if we ever decipher its language, we might not just solve a quantum puzzle. We could unlock the universe's operating manual, written in threads of frozen light. Symmetry isn't just about beauty, it's the silent architect of reality, a hidden hand shaping everything from snowflakes to galaxies. But what happens when we strip away all heat, all motion, leaving only the barest skeleton of existence? At absolute zero, symmetry doesn't just persist, it might ascend to perfection, revealing a blueprint written into the fabric of nothingness itself. Picture a frozen lake at dawn, its surface so still it mirrors the sky flawlessly. That's the kind of pristine symmetry we're talking about, a state where the universe's underlying order shines through, unspoiled by the usual chaos of temperature and motion. Take the laws of physics themselves. They're brimming with symmetries, like the way a spinning top looks identical from every angle, or how the forces governing particles don't care if you're in Tokyo or on Mars. These aren't accidents, they're deep clues about how reality is structured. Near absolute zero, where atoms settle into their lowest possible energy states, these symmetries can become even more pronounced. Superconductors, for example, exhibit something called gauge symmetry, a kind of mathematical harmony where electrons move in lockstep, as if orchestrated by an invisible conductor. It's as if the cold peels back a layer of noise, letting the universe's true symmetry sing clearly for the first time. But here's where it gets cosmic. The quantum vacuum, that seething nothingness we've been exploring, might owe its very existence to symmetry. According to quantum field theory, the vacuum isn't truly empty because symmetrical laws demand it buzz with activity. Imagine a perfectly balanced seesaw. Even when it's level, there's tension, potential energy waiting to tip. The vacuum is like that. Its symmetries generate the zero-point energy we observe, the restless flicker of particles that refuse to let emptiness be truly empty. Some theories even suggest that the Higgs field, which gives particles their mass, emerged from a broken symmetry in the early universe, like a vase shattering into fragments, each piece still hinting at the whole it once was. This isn't just abstract math. Symmetry might explain why the universe looks the way it does. After the Big Bang, why did matter dominate antimatter, allowing stars and planets and us to exist? The answer could lie in asymmetries buried in the quantum vacuum, tiny imperfections frozen into reality's foundation like cracks in ice. And at absolute zero, where thermal agitation fades, these cracks might become visible, etched into the behavior of ultra-cold matter like cosmic fingerprints. So what's the grand takeaway? Symmetry isn't just a feature of the universe, it's the scaffolding. From the quantum vacuum's hidden order to the large-scale structure of space-time, symmetry shapes the void as surely as it shapes the stars. And the colder we go, the clearer that architecture becomes, whispering secrets about how something as seemingly simple as balance could be the key to everything. Negative temperatures sound like a contradiction. How can something be colder than the coldest possible state? Yet in the bizarre world of quantum physics, certain systems don't just approach absolute zero, they plunge right past it, flipping our understanding of heat and cold on its head. Picture a thermometer that doesn't stop at zero but keeps dropping into negative numbers, as if the scale itself has turned inside out. This isn't a glitch in the math, it's a real phenomenon observed in ultra-cold labs, where atoms are coaxed into states so strange they redefine what temperature even means. At first glance, temperature seems straightforward. It measures how much particles jiggle. Absolute zero is the point where all motion stops, the end of the line. But dig deeper and you'll find temperature isn't just about motion, it's about probability. Normally, most particles in a system occupy low-energy states with a few excited outliers. But in certain engineered setups, like lasers or magnetic fields, physicists can flip this distribution, forcing more particles into high-energy states than low ones. When this happens, the system's temperature doesn't just hit zero, it overshoots, becoming negative. It's as if you filled a stadium so packed that more people are crammed into the nosebleed seats than the front row. The rules haven't broken, they've just revealed a hidden door. What's wild is how these negative temperature systems behave. Instead of absorbing energy, they can spontaneously emit it, acting like cosmic batteries. Some even defy gravity, with atoms that seem to repel rather than attract one another. These aren't just laboratory curiosities. They hint that the quantum vacuum might harbor similar inversions, layers where nothing isn't passive but primed to release energy in ways we've yet to imagine. Think of it like a frozen lake that, when tapped just right, starts boiling without heat. This twists our view of nothingness. If temperatures can go negative, then absolute zero isn't a wall, it's a threshold, a gateway to stranger realms where energy flows backward and particles dance to an inverted rhythm. The void might not be empty after all, but a hall of mirrors reflecting possibilities we're only beginning to trace. And if we ever learn to harness these states, we could unlock technologies that seem like magic today, engines that run on cosmic cold, or materials that defy entropy itself. The coldest cold isn't the end. It might just be the beginning. Cosmic inflation wasn't just an explosion, it was a revolution, rewriting the rules of space itself in a fraction of a second. Picture the universe in its infancy, smaller than a single atom, when suddenly it stretched faster than light could chase it, ballooning to cosmic proportions in less time than it takes to blink. This wasn't expansion as we know it today. It was space-time itself being pulled taut like hot taffy, smoothing wrinkles and stretching quantum ripples into the seeds of galaxies. But here's the twist. While inflation stretched matter and energy, it also stretched nothingness, imprinting the void with a hidden topography we're only now learning to read. Those primordial quantum fluctuations, tiny hiccups in spacetime's fabric, were frozen into the universe's blueprint during inflation, like footprints pressed into wet cement. Today, they show up as faint temperature variations in the cosmic microwave background, the afterglow of the Big Bang, but these aren't just random bumps. They're echoes of the void's original structure, a fossil record of how emptiness itself was sculpted in those first frantic moments. Some theories suggest these fluctuations weren't confined to matter alone. They might have warped the quantum vacuum too, creating pockets where dark energies influence very subtly, like invisible hills and valleys in the fabric of space. Think of it like blowing up a balloon with ink dots on its surface. As the balloon inflates, the dots spread apart, but their pattern preserves information about the balloon's original shape. Inflation did the same to space-time, magnifying quantum jitters into cosmic scale undulations. The mind-bending part, those jitters weren't just in space, they were space, fluctuations in the very geometry of nothingness. Today, when we map the distribution of galaxies across billions of light years, we're seeing the stretched-out shadows of those primordial tremors, a web of structure woven into the void itself. But inflation's legacy might go deeper. Some models propose that the rapid stretching didn't just smooth the universe, it could have left behind defects in spacetime's fabric, like cracks in ice. These cosmic strings or domain walls, if they exist, would be threads of pure energy thinner than a proton but stretching across the cosmos, where the vacuum's properties abruptly shift. Imagine walking through a forest and suddenly hitting an invisible wall where the trees on one side subtly twist in a different direction. That's what spacetime might be like near these relics, regions where nothingness itself has a seam. The stakes couldn't be higher. If we can decode inflation's fingerprints in the void, we might finally understand why the universe looks the way it does. Why is matter clustered just so, with galaxies strung along filaments like pearls on a necklace? Why does dark energy's push seem so eerily balanced, as if fine-tuned by some unseen hand? The answers could lie in those first moments when the void wasn't empty, but pregnant with potential, its architecture being forged in the fire of exponential expansion. And as we peer deeper into the cosmos' coldest, quietest corners, we're not just studying space, we're reading the diary of nothingness, written in the language of quantum frost. The universe shouldn't work, at least not for us. Tweak the strength of gravity by a hair, nudge the charge of an electron, or adjust the quantum vacuum's energy density by even a whisper, and stars wouldn't form, atoms would fly apart, and life as we know it would be impossible. Yet here we are, in a cosmos where the void's architecture, its hidden symmetries, quantum fluctuations, even the eerie precision of absolute zero, creates conditions so finely tuned they border on miraculous. This is the anthropic principle in action, the idea that the universe's laws appear perfectly calibrated for life because, well, we're here to notice. But peel back that surface-level explanation and you'll find a deeper mystery. Why does nothingness, the quantum vacuum, dark energy, the frozen silence of space play along so perfectly? Take the cosmological constant, that measure of the vacuum's energy density. If it were slightly stronger, the universe would have ripped itself apart before galaxies could form. Slightly weaker, and gravity would have crushed everything back into a singularity. Instead, it's balanced on a knife's edge, as if the void itself was designed with life in mind. Some physicists argue this isn't coincidence but necessity, that in a multiverse of infinite possibilities, we naturally find ourselves in one of the rare universes where the void's parameters allow complexity to emerge. It's like winning the cosmic lottery, except the prize isn't money but existence itself. But there's another, more provocative take. What if the void isn't just accommodating life but somehow entangled with it? Consider how quantum fluctuations in the early universe, those tiny ripples in nothingness, became the seeds for galaxies, or how the absolute zero behavior of matter superconductivity, superfluidity mirrors the kind of delicate coordination life relies on at the molecular level. It's as if the universe's emptiest corners and its most intricate structures are playing by the same hidden rules. even consciousness, that most enigmatic of phenomena, might tap into the quantum vacuum's latent activity, with some theorists suggesting our minds could be receivers tuned to the void's subtle frequencies. This isn't just philosophy. Experiments with ultra-cold quantum systems show that particles behave differently when observed, as if awareness itself nudges the void's architecture. And if dark energy's push is indeed tied to the quantum vacuum, then the expansion of the cosmos, the very stage on which life unfolds, is choreographed by nothingness. The unsettling implication: we're not just bystanders in a preordained universe. The void's fine-tuning might be a mirror, reflecting back the strange truth that reality and observer are inextricably linked. So is the void's perfection a fluke or a clue? Either way, one thing's certain: the silence of space isn't silent at all. It's a conversation, one we're only beginning to hear. Neutrinos are the universe's ultimate ghosts, particles so elusive they slip through planets like sunlight through glass. Born in the hearts of stars, supernova, and even the decay of atoms in your own body, these nearly weightless phantoms barely interact with matter at all. 1 trillion neutrinos pass through your fingertip every second, leaving no trace, as if the solid world around you is nothing more than a faint mist. But what if this ghostly nature isn't just a quirk of physics? What if neutrinos are whispering secrets about the hidden architecture of nothingness itself? Think of the quantum vacuum as a vast, invisible ocean, its surface ruffled by the constant flicker of virtual particles. Most particles, electrons, quarks, even light are like boats bobbing on those waves, pushed and pulled by the ocean's hidden currents. Neutrinos, though, are different. They're more like gusts of wind slicing through the water without leaving a ripple. Their near-total lack of interaction with matter suggests they might be skating along the seams of space-time, brushing against the void's structure in ways we can't yet measure. Some theories propose that neutrinos don't just ignore matter. They might be sensitive to the quantum foam's subtlest vibrations, acting as cosmic messengers from realms where ordinary particles dare not tread. Consider this: when a star collapses into a supernova, it doesn't just explode outward in a burst of light. It screams in neutrinos, releasing more of these particles in a single cataclysm than there are stars in the Milky Way. Yet by the time those neutrinos reach Earth, they've crossed light years of space without slowing, without scattering, as if the universe itself is barely there to them. It's as though neutrinos are tuned to a frequency most of reality can't hear, moving through dimensions or layers of the vacuum that remain invisible to us. Experiments like IceCube, which hunts for neutrinos deep in Antarctic ice, have caught glimpses of these particles arriving from distant cosmic disasters with energies that defy explanation, hints that neutrinos might be tapping into something far stranger than empty space. Here's where it gets speculative and thrilling. If neutrinos interact with the quantum vacuum's hidden scaffolding, even faintly, they could be our first clue to a shadow universe woven into the void. Some models suggest that certain types of neutrinos might oscillate between flavors not just because of mass differences, but because they're dancing with unseen fields permeating the vacuum. Others propose that high-energy neutrinos could reveal cracks in spacetime's geometry, places where the void's smooth facade frays into extra dimensions or quantum knots. Even dark matter, that other great cosmic mystery, might be linked to neutrinos through the vacuum's secret channels, with the two communicating in ways we're only beginning to imagine. The irony is exquisite. To study nothingness, we might need to chase the most untouchable somethings in existence. Neutrinos don't just pass through matter, they pass through our understanding, leaving behind a trail of questions. Every time we detect one, it's like catching a whisper from the dark, a reminder that the void isn't empty. It's alive with possibilities, and neutrinos might be the only ones fluent in its language. If we ever learn to listen, we might finally hear what nothingness has been trying to tell us all along. The Casimir effect isn't just a laboratory curiosity, it's a cosmic wake-up call that the void has teeth. Picture two smooth metal plates hovering nanometers apart in a perfect vacuum, far from any obvious force. Yet against all intuition, they snap together as if pulled by invisible strings. This bizarre phenomenon occurs because the space between them isn't empty at all. The quantum vacuum thrums with fleeting particles that pop in and out of existence like bubbles in a fizzy drink. Normally, these virtual particles appear in all wavelengths, pushing equally from all directions. But when plates get extremely close, longer wavelengths can't fit between them, creating a pressure imbalance. The result, nothingness itself becomes a puppeteer, nudging solid objects with measurable force. This effect reveals something startling about the universe's scaffolding. If an empty space can push plates together, what other invisible machinery might be humming beneath reality's surface? Some theories suggest similar quantum pressure could operate on cosmic scales, influencing how galaxies cluster or how dark energy stretches spacetime. Imagine the voids between galaxy clusters not as passive expanses but as quantum foam under tension, subtly herding matter into filaments and walls. The Casimir force is tiny between lab plates, but magnified across light years. Such effects might sculpt the large-scale structure of everything. Even stranger are the theoretical extensions of this phenomenon. Certain models predict that under extreme conditions like near-spinning black holes or in hypothetical warp drive geometries, the quantum vacuum's energy could be amplified into repulsive forces, effectively making nothingness a propellant. Picture a spacecraft surfing waves of pure void energy, pushed forward by the universe's own restless baseline. While this remains speculative, the underlying principle is concrete. The vacuum isn't inert. It's a dynamic medium capable of exerting influence we're only beginning to map. The real magic happens when we ask why this matters beyond textbook physics. The Casimir effect forces us to confront that every empty volume around us, the air between your screen and eyes, the space inside atoms themselves, is actually a seething quantum arena. What we perceive as stillness is a misdirection, a cosmic sleight of hand where the fundamental hustle of existence never stops, only hides. When two plates move under vacuum pressure, they're not breaking nature's rules. They're revealing the game was rigged from the start, with nothingness as the ultimate house, always dealing from the bottom of the quantum deck. Quantum tunneling is the universe's greatest escape act, particles slipping through walls like ghosts, vanishing on one side of an impossible barrier and reappearing on the other without a trace. In the everyday world, this would be like throwing a ball at a mountain and watching it suddenly materialize on the far slope. No impact, no climb, just an effortless leap through solid rock. According to classical physics, this shouldn't happen. Energy is supposed to be conserved, barriers are meant to block. Yet at the quantum scale, the rules rewrite themselves, and particles routinely pull off this vanishing trick. The secret might lie not in the particles themselves, but in the silent, seething architecture of nothingness beneath them. Picture an electron trapped in a box, a tiny prison of energy walls it lacks the strength to climb. In a predictable universe, it would stay there forever, but the quantum vacuum isn't predictable. It's a froth of potential where particles flicker in and out of existence, borrowing energy from nowhere and paying it back in fractions of a second. When an electron tunnels, it's not brute forcing its way through the barrier. Instead, it's hitching a ride on these quantum fluctuations, surfing the void's restless waves to emerge unscathed on the other side. It's as if the vacuum itself provides a hidden tunnel, a backdoor written into the fine print of reality. This isn't just theoretical sleight of hand. Tunneling is the reason the sun shines. Deep in its core, protons that should repel each other due to their identical charges instead fuse together, powering stellar fires. Without quantum tunneling, those protons would never overcome their mutual repulsion, and stars, including ours, would flicker out. Even your own DNA relies on tunneling. Enzymes in your cells use it to speed up chemical reactions, making life's vital processes possible. The void isn't just allowing these feats, it's enabling them, as if the universe built loopholes into its own laws. But here's the twist: tunneling might not be limited to tiny particles. Some interpretations suggest that if the quantum vacuum can bend the rules for electrons, it could theoretically do the same for larger objects, even you. The odds are astronomically low, but non-zero. Given enough time, a person could spontaneously tunnel through a wall, though you'd likely wait longer than the age of the universe for it to happen. Still, the mere possibility hints that nothingness isn't a blank slate. It's a dynamic medium humming with probabilities where impossible is just a matter of statistics. So what's really happening when particles tunnel? One radical idea is that they're not moving through space at all, but slipping between moments, exploiting gaps in time itself. Or perhaps the vacuum structure contains folds or shortcuts, like wrinkles in a carpet, letting particles skip across barriers the way a needle might pass through fabric without breaking the threads. Whatever the answer, tunneling forces us to confront that emptiness isn't passive. It's an active participant, a silent collaborator in the universe's most astonishing tricks. And every time a particle cheats the odds, it's not breaking nature's rules, it's revealing how deep they really go. Dark matter doesn't just lurk in the shadows, it builds them. Imagine the cosmos as a vast, invisible spiderweb. Its strands too fine to see but strong enough to catch entire galaxies in their grip. This isn't science fiction. We know dark matter exists because without its gravitational pull, galaxies would fly apart like shattered glass. Stars orbit their centers too fast for the visible matter alone to hold them, as if something unseen is clenching its fists around them. But what if dark matter's influence doesn't stop at galaxies? What if it threads through the emptiest reaches of space, stitching the void itself into a hidden architecture? Picture a cosmic construction site. The bright galaxies and glittering stars are just the finished buildings, the flashy skyscrapers that catch your eye. Dark matter, though, is the steel girders and scaffolding, the unseen framework holding everything together. In the voids between galaxies, where light barely travels and matter is almost absent, dark matter might form delicate filaments, a lattice of gravity stretching across billions of light years. These aren't just empty corridors, they're highways of influence, shaping how galaxies move and clusters form. Simulations of the universe show this faint webbing clearly, dark matter's tendrils guiding the growth of everything we can see, like invisible roots feeding a forest. Here's where it gets stranger. Some theories suggest dark matter isn't just passive scaffolding. It could be dynamic, interacting with itself or the quantum vacuum in ways we've yet to detect. Certain models propose that dark particles might decay or collide, releasing energy that subtly heats the void. Others imagine dark matter as a kind of cosmic glue, its gravitational field stabilizing the quantum foam, preventing space-time itself from fraying at the seams. If true, then the emptiest parts of the universe aren't truly empty. They're saturated with dark matter's quiet presence, a scaffold so pervasive it's woven into the fabric of nothingness. The most tantalizing clues come from the way galaxies move. In vast cosmic voids where visible matter is almost absent, galaxies sometimes drift with peculiar speeds, as if tugged by something unseen. Dark matter's gravitational whispers could explain these anomalies, its tendrils reaching even into the deepest voids to pull strings we can't see. Telescopes mapping the cosmic microwave background, the afterglow of the Big Bang, have spotted faint imprints that might be dark matter's fingerprints, subtle warps in spacetime that trace its hidden architecture. But the real mystery is what this means for the void's true nature. If dark matter structures emptiness, then nothing is an illusion. The universe's darkest corners might be its busiest construction zones, where invisible forces sculpt reality in silence. And if we ever learn to map this shadow scaffolding, we won't just solve a cosmic puzzle, we'll uncover the blueprint of existence itself, written in the language of the unseen. The Boltzmann brain is a paradox so unsettling it makes the hair on your neck stand up. What if everything you know, every memory, every sensation, isn't real at all, but a fleeting hallucination conjured from the void's random chaos? Picture this: in the vast, cold expanse of an infinite universe where time stretches endlessly, the quantum vacuum's restless flickers could, by sheer chance, arrange particles into a fully formed, self-aware mind. Not a brain born of evolution or biology, but a momentary spark in the dark, a thinking entity that blinks into existence just long enough to wonder, why am I here? Before dissolving back into the abyss, this isn't science fiction. It's a brutal clash between physics and philosophy, forcing us to ask, in a cosmos where nothingness can't sit still, is consciousness the exception, or just another ripple in the quantum foam? The idea stems from thermodynamics, specifically Ludwig Boltzmann's work on entropy. In an infinite universe, even the most improbable events must happen eventually, like a tornado assembling a fully functional jet engine from a junkyard. Given enough time, random fluctuations could theoretically cobble together a functioning brain, complete with fabricated memories of a life never lived. The real kicker, statistically, it's far more likely for a single, isolated brain to pop into existence than an entire, ordered cosmos like ours. So by that logic, you are probably the Boltzmann brain, not the other way around. It's a cosmic gut punch. The universe you perceive might just be a glitch, a mirage woven from the void's aimless fidgeting. But here's where the thought experiment twists the knife. If the void can spontaneously birth awareness, then consciousness isn't special, it's inevitable, an accidental byproduct of infinite time and infinite emptiness. This flips the anthropic principle on its head. Instead of the universe fine-tuning itself for life, life becomes a statistical fluke, a temporary hiccup in the void's indifferent hum. Some physicists dismiss Boltzmann brains as absurd, arguing that if they were possible, we'd be drowning in them, their fleeting thoughts outnumbering real minds trillions to one. Others counter that maybe we are drowning in them, and every phantom consciousness winks out before it can leave a trace. The implications bleed into reality itself. If a Boltzmann brain can't tell its fabricated world from the real one, how do we know we're not one? Descartes' "I think, therefore I am" crumbles when the "I" might be a cosmic typo, a thinking mistake scribbled in the margins of nothingness. It's a hall of mirrors problem. The harder you stare, the less certain you become. Quantum mechanics offers no comfort. Observation shapes reality. But what if the observer is just another quantum fluctuation? Here one Planck second, gone the next. Yet buried in this existential vertigo is a strange hope. If the void can accidentally create a mind, then consciousness might be woven into the universe's fabric, a latent possibility waiting in the cold and dark. The Boltzmann brain isn't just a horror story, it's a testament to the void's creativity, its ability to spin gold from chaos. And that raises one last chilling question. If nothingness can dream, what else is it dreaming up? White holes defy logic in the most spectacular way. Imagine a black hole running in reverse, not devouring matter but violently ejecting it, like a cosmic fire hose blasting reality outward at impossible speeds. While black holes trap even light behind their event horizons, white holes would theoretically do the opposite. Nothing could enter, only escape. They're the universe's ultimate one-way exit doors, spewing energy and matter with such force that approaching them would be like trying to swim up a waterfall made of space-time itself. Yet for all their theoretical drama, no white hole has ever been observed. They exist as shimmering mirages in the equations of general relativity, mathematical mirror images of black holes that tantalize physicists with their possibility. What makes white holes so compelling isn't just their violence, it's their potential to rewrite the life cycle of nothingness. If black holes are the end of things, white holes could be the beginning. Some theories suggest that when a black hole's gravitational collapse reaches its limit, it might rebound as a white hole, transforming the crushing singularity into a fountain of new energy. Picture a deflated balloon suddenly reinflating with explosive force, or a dying star reigniting in reverse. This quantum bounce could mean that what we call emptiness isn't eternal, it's a phase, a momentary pause before the void reboots itself. There's even wilder speculation. Could our own Big Bang have been the ultimate white hole event, a primordial eruption of space-time from some other universe's collapsed remains? If so, then the vast cosmic voids we see today might not be passive emptiness, but the echoes of earlier cycles of collapse and rebirth. The quantum vacuum's seething energy could be the residual spark of a white hole's aftermath, like embers lingering after a fireworks burst. But here's the catch. White holes violate the second law of thermodynamics, which states entropy always increases. A universe where white holes exist would need a way to reconcile their explosive order with the relentless march toward chaos. Some physicists argue that white holes could be fleeting, their outbursts lasting only fractions of a second before succumbing to entropy. Others propose they're hidden behind event horizons of their own, their fireworks display invisible to outside observers. The most tantalizing clue might lie in fast radio bursts, those mysterious, ultra-powerful blasts of energy from deep space. A handful of scientists have dared to suggest these could be white holes flickering to life and vanishing just as quickly, cosmic geysers erupting from the fabric of spacetime itself. It's a stretch, but if proven, it would mean the void isn't just empty or chaotic. It's generative, capable of spitting out new reality as easily as it swallows the old. So why does this matter? Because white holes challenge our deepest assumptions about nothingness. If even the void can reboot, then emptiness isn't an end, it's a comma, a pause in a sentence we're still learning to read. And if we ever find proof of these cosmic reversals, we won't just be discovering a new object. We'll be glimpsing the universe's secret rhythm, the heartbeat of nothingness itself. Heat death sounds like the universe's final sigh, a slow, inevitable fade into darkness where every star burns out, every proton decays, and even black holes evaporate into whispers of radiation. Picture a cosmos stretched so thin that temperatures plunge near absolute zero, a frigid stillness where nothing moves, nothing changes, and nothing remembers. It's the ultimate triumph of entropy, where energy disperses so evenly that no work can be done, no light can shine, and no thought can flicker. But here's the haunting twist. This frozen, lifeless state isn't just an end. It's a mirror of the void we've been exploring all along. The same quantum vacuum buzzing with potential today could one day become the universe's silent tomb, a vast, featureless desert where time itself loses meaning. Yet the irony is exquisite. The heat-death scenario isn't a story of fiery destruction, but of cold, perfect balance. In this distant future, the cosmos won't explode or collapse. It will simply exhale, settling into a state so uniform that differences cease to exist. No more galaxies, no more particles colliding, just an endless sea of equilibrium where the concept of something loses all distinction from nothing. It's as if the universe, after billions of years of complexity, finally returns to its original blueprint, the pristine silence of absolute zero. But is this truly an ending, or just another phase in a cycle we don't yet understand? Some theories suggest that even in this frozen oblivion, the quantum vacuum's restless energy might persist. Virtual particles could still flicker in the dark, borrowing energy from spacetime's last dregs, their brief lives the only motion in an otherwise motionless cosmos. If so, then heat-death isn't the absence of activity, it's activity stripped to its barest essence, a universe reduced to its quantum skeleton. And if the void can birth particles from nothing today, who's to say it couldn't spark a new Big Bang in the far, far future? Imagine a cosmic reset button hidden in the cold. After countless eons, a random fluctuation might twist spacetime so violently that a new universe bubbles forth, inflating from the ashes of the old. This cyclical vision challenges our linear notions of time and endings. Perhaps heat-death isn't a finale but a hibernation, a pause before the void stirs again. After all, if absolute zero isn't truly empty, if it's a seething potential masked by perfect balance, then even the universe's coldest, darkest epoch might be pregnant with possibility. The same quantum rules that let particles tunnel through barriers or pop into existence could, given enough time, rewrite the cosmos' fate. So is nothingness the end? Or is it the universe's way of holding its breath, waiting for the next act to begin? The answer might lie in the void's deepest paradox, that emptiness is never truly empty, and silence never truly still. Even at the end of time, the void's blueprint remains, etched into the fabric of reality, waiting. Long before quantum fluctuations and dark energy entered the scientific lexicon, the void was already haunting human thought. Ancient Greek philosophers like Parmenides argued that nothingness couldn't exist after all. To speak of nothing was to give it a kind of being. Meanwhile, Buddhist traditions embraced sunyata, the concept of emptiness as the fundamental nature of reality, where all phenomena arise interdependently without inherent existence. These early musings weren't just abstract poetry, they were grappling with the same paradoxes that keep physicists awake today. How can nothing be a generative force? Why does the universe seem built on absence as much as substance? Fast forward to the 17th century, when French philosopher René Descartes famously declared, "I think, therefore I am," anchoring existence in consciousness while treating the external world, including empty space, as suspect. Yet just decades later, Isaac Newton's physics would reify the void, framing it as an absolute stage where particles moved like actors under gravity's direction. This tension between nothingness as abstraction and nothingness as physical reality never resolved, it merely evolved. Existentialists like Jean-Paul Sartre later framed nothingness as the gap between human expectation and a silent, indifferent universe, a void we fill with meaning through sheer will. Today's physics offers startling echoes of these ideas. When quantum field theory describes particles emerging from vacuum fluctuations, it mirrors ancient creation myths where form arises from formlessness. The holographic principle's suggestion that reality projects from a 2D boundary recalls Platonic idealism, where the tangible world is a shadow of deeper truths. Even dark energy's mysterious push aligns with Heidegger's concept of the nothing as an active, unsettling force rather than mere absence. The through line is uncanny. Whether through metaphor or mathematics, humans keep circling the same realization: emptiness isn't inert. It's dynamic, a participant in creation. The most provocative overlap lies in consciousness studies. Some interpretations of quantum mechanics suggest observation collapses probability waves into reality, implying mind and void are entangled. This isn't far removed from Eastern philosophies where perceiver and perceived co-create existence. Meanwhile, neuroscientists probing near-death experiences describe encounters with voids that patients insist felt profoundly alive, an eerie parallel to the quantum vacuum's latent energy. Whether through meditation or particle colliders, we're drawn to the same threshold, the point where nothingness reveals itself as pregnant with potential. Critics argue these connections are just poetic analogies, that physics deals in measurable quantities while philosophy traffics in the unquantifiable. But the boundaries blur when you consider how both disciplines confront the limits of language. Quantum physicists speak of particles being neither here nor there until measured, while Zen masters describe reality as not one, not two. Both are straining toward truths that defy binary logic. Perhaps the void's greatest lesson is that our categories, physical versus metaphysical, something versus nothing, are themselves illusions, artifacts of a mind evolved to navigate middle scales, not cosmic or quantum depths. What emerges is a dialogue spanning millennia, where the oldest questions about absence and existence find new life in cutting-edge labs. The void isn't just a scientific frontier or a philosophical riddle, it's the mirror where both reflect each other, revealing how deeply our search for meaning is woven into the fabric of reality. And every time we peer into the abyss, we're not just studying nothingness, we're discovering what it means to be something. Harnessing the quantum vacuum isn't science fiction, it's a frontier where tomorrow's technology is already taking shape. Picture a world where energy isn't mined or manufactured but extracted from the empty space around us, where materials defy gravity not through brute force but by dancing with the void's hidden rhythms. This isn't fantasy. Labs worldwide are edging toward these breakthroughs by probing the strange behaviors of matter near absolute zero. Take superconductors, those remarkable materials that, when chilled sufficiently, conduct electricity with zero resistance. Today they require extreme cold, but imagine if we could engineer room temperature versions. Suddenly, power grids would operate without energy loss. MRI machines would become exponentially more precise, and maglev trains could glide effortlessly across continents. The key lies in deciphering how the quantum vacuum mediates these phenomena, not as passive background, but as an active participant in material properties. Even more revolutionary is the concept of vacuum energy extraction. The Casimir effect proves that empty space exerts real, measurable force. So what if we could amplify or redirect that force? Theoretical models suggest nanostructured materials might one day trap virtual particles, converting the vacuum's restless energy into usable power. While skeptics argue this violates thermodynamic laws, others point to quantum anomalies like dynamic Casimir effects, where rapidly moving mirrors in a vacuum actually produce photons from nothingness. It's as if the void itself can be persuaded to give up its secrets under the right conditions. Projects like DARPA Quantum Vacuum Plasma Thruster hint at military interest in these possibilities, though mainstream applications remain decades away. Then there's the tantalizing potential of quantum levitation. When certain materials are cooled to extreme temperatures, they don't just superconduct, they lock magnetic fields in place, allowing objects to hover indefinitely above magnets. This isn't mere magnetic repulsion, it's the material exploiting quantum effects to freeze magnetic flux lines in the vacuum around it. Scale this up, and you're looking at frictionless bearings for space stations, ultra-efficient energy storage, or even vehicles that glide on invisible quantum rails. The underlying principle, the void isn't empty, it's a lattice of untapped forces waiting to be harnessed. Perhaps most mind-bending are proposals to engineer spacetime itself. If the vacuum's energy density can be manipulated, say, through precisely controlled electromagnetic fields, we might one day create localized warp bubbles, regions where space contracts ahead of an object and expands behind it. While this sounds like Star Trek fantasy, NASA Eagleworks Lab has explored preliminary designs for warp drives based on quantum vacuum manipulations. The challenges are monumental, but the physics doesn't forbid it. After all, the universe already performs this trick naturally with dark energy's cosmic expansion. We'd just be learning to speak the void's language fluently enough to request a reroute. The coldest cold might also rewrite computing. Quantum computers currently require near absolute zero temperatures to maintain coherence, their qubits shielded from thermal noise by elaborate freezers. But what if we could simulate those pristine quantum conditions at higher temperatures by mimicking the vacuum's structure? Researchers are experimenting with topological materials whose electron behavior mirrors the quantum vacuum's geometry, potentially enabling stable qubits without extreme cooling. This could democratize quantum computing, transforming it from a lab curiosity to a household tool. None of these applications will emerge overnight. The void guards its blueprints jealously, revealing them only through painstaking experimentation and theoretical daring. Yet the trajectory is clear. As we decode nothingness architecture, we're not just observing nature, we're learning to collaborate with it. The ultimate irony, humanity's most advanced technologies might not come from conquering matter, but from finally understanding the art of emptiness. The architecture of nothingness isn't just an absence, it's a hidden dimension of reality, brimming with structure and possibility. Think of the void not as empty space, but as a cosmic canvas where the faintest brushstrokes of quantum energy paint the scaffolding of existence itself. Every flicker of a virtual particle, every tug of the Casimir effect, every whisper of dark energy reveals that what we call nothing is, in truth, the universe's most intricate construction site. Absolute zero isn't the end of motion, it's the stage where reality's deepest laws perform their quietest, most elegant dance. Consider how far we've come in peeling back the layers of this mystery. Just a century ago, emptiness was thought to be just that, empty. Now we know better. The quantum vacuum hums with potential, a seething sea of particles that blink in and out of existence, borrowing energy from the fabric of spacetime itself. Dark energy stretches the cosmos like an invisible hand, while entangled particles defy distance, their connection woven into the void's hidden architecture. Even the coldest reaches of space, where temperatures plunge near absolute zero, aren't still. They're alive with superconductivity, superfluidity, and phenomena that twist our understanding of physics into knots. But the most thrilling part, we're only scratching the surface. Every breakthrough raises new questions. Could the void's structure hold clues to unifying gravity and quantum mechanics? Might it reveal the origins of consciousness itself, or the true nature of time? The closer we look, the more we realize that nothingness isn't a void, it's a mirror, reflecting back the limits of our understanding and daring us to look deeper. So where do we go from here? The next frontier lies in pushing our experiments further, chilling matter to even lower temperatures, probing the quantum vacuum for signs of new physics, and listening for the faint echoes of cosmic strings or white holes in the darkness. The void isn't just a subject of study, it's a collaborator challenging us to rethink everything we thought we knew. What do you think lies at the heart of nothingness? Is it the seed of new universes, the key to dark energy, or something stranger still? Drop your theories in the comments. We're all explorers here, piecing together the universe's grandest puzzle. And if you're hungry for more deep dives into the mysteries of space, time, and beyond, hit that subscribe button. The universe's secrets aren't going to uncover themselves. Let's keep searching together.